I am Anil Kumar. Welcome to my series on rational functions. In its first chapter, we learned about reciprocal functions. Now here we have 4 open response test questions for you. I would like you to copy these questions, answer them, and then look into my solutions. Now here is question number 1, where you need to provide example for each of the following reciprocal function. Sketch both function and its reciprocal. Now these 4 examples will help you understand the topic far better. The first one is a reciprocal function where horizontal asymptote does not exist. B is a reciprocal function where vertical asymptote does not exist. C is a reciprocal function which is always increasing in its domain, and D is a reciprocal function continuous in the domain of real numbers. Here is question number 2. You need to sketch graph of f of x equals to 1 over x cubed minus 3x minus 2. Now, it's reciprocal of a cubic function. You may use factor theorem to factor and then sketch the graph. Question number 3 is actually related with question number 2. Once you sketch the graph of the function, you need to describe its characteristics. Mainly domain, range, vertical asymptotes, horizontal asymptotes, increasing interval, decreasing interval, and when is the function positive or negative. Here is question number 4. Sketch the function f of x and its reciprocal g of x. F of x should satisfy each of the following. So the properties are given of the function. You have to sketch its reciprocal. So properties of the function is that it has 2 x-intercepts. It is increasing in the interval from 0 to 2, decreasing in the interval from minus 2 to 0, and it has absolute maximum value of 4. In case you need help, you can always look into the links provided, review the chapter on reciprocal functions, and then watch the solution of my questions. I hope that helps. I'll be back with the solutions now. Now one by one, let's look into the solutions. Question number 1. Provide example for each of the following reciprocal function. Sketch both function and its reciprocal. Horizontal asymptotes does not exist. So that is the very first one. So what could be the criteria where horizontal asymptote will not exist? So basically the graph of the function should not approach positive or negative infinity, right? That's the whole idea. So if that is the case, then we will not have horizontal asymptotes, right? So the characteristics which we are looking for is that the function f of x, so I'll actually sketch function in green. So if I have a function whose range is limited, in that case we'll not have horizontal asymptote. So one of the examples could be semicircle. Now semicircle is a good function to match the criteria, correct? So if you are supposed to provide with the equation, you can always say it is y equals to square root of, we are taking only the positive part, and let's say these values here are minus 1 and 1. This could be 1, right? So it is 1 minus x square root. So that could be the function, right? And the reciprocal of this function will be, let's call it g of x. Reciprocal of this function will be 1 over square root of 1 minus x square. Well, it is not necessary to give the equations, but this is a very important function, and that's why I provided you with these equations. Now, at the x-intercepts, we expect vertical asymptotes. So that becomes the vertical asymptote for g of x, which is shown in red here, right? Reciprocal of 1 is 1, so this point will coincide, and positive reciprocal is going to be positive, so it will be kind of like this. You can clearly see that there is no horizontal asymptote. Perfect. Now let's look into second. Vertical asymptotes does not exist. So the vertical asymptote will not exist if we do not have any x-intercept, right? So that's the concept. So let me sketch a function here, which is a parabola, let's say, right? So let's sketch a parabola, which is, let us say, kind of like this. This time I've sketched the function in red. So this time my function f of x is, let us say, x squared plus, let me write this time 2. So if I take this value as 2, in that case, let me take this as half, right? So I'll give you a better graph. So let me take this value as not 2 but half. Okay, so that will help me to show some more characteristic. That's the whole idea. Let's say this is 1, right? So if this is 1, then these are invariant points, right? And reciprocal of half is 2. So we'll have a function which will be having a absolute maximum of 2, right? So it will be kind of like this is half, 1, and kind of like this, going through this value of 1. So it will be kind of like this bell-shaped graph, right, where this is 2. So in this case, we have g of x, which is equal to 1 over x squared plus half, right? So that is going to be the function, and you can clearly see here we do not have any vertical asymptote. Domain is all real numbers, correct? Next one is always increasing in its domain, right? So many functions could be drawn to match this condition, always increasing in its domain. One of them could be what? Minus 1 over x, right? So if we want always increasing, we could have a line which is decreasing, right? So if I have a line which is decreasing, for example, in that case, let's say, let me sketch this time the graph of a line in green. So a decreasing line will result into increasing function. That's the whole idea, correct? Decreasing line will result into increasing reciprocal function. So x-intercept will give us the vertical asymptote, and the graph of the function will be like this. As you can see, it is always increasing in its domain, right? So we can label these points as 1 and 1. Example could be y equals to minus x, and g of x equals to minus 1 over x is a function which is always increasing in its domain, right? Of course, x is not equal to 0, right, for the reciprocal function. Part D is continuous in the domain of real numbers. So you could again sketch a function like 1 over x squared plus 1. So that function, let's say equals to g of x, will look similar to this, right, which you could sketch for the last example. So let me just sketch it here. So we could have a parabola this time whose vertex is at 1, right? So x squared minus 1, and 1 reciprocal is 1, so we'll get a function which is kind of like this, and that is g of x. So that is how you could provide examples in the given situation. Now that should help you to grasp all the things which you missed out earlier while getting through the reciprocal functions. I hope that helps. Now let's move on to question number 2. Question number 2 sketch graph of the function 1 over x cubed minus 3x minus 2. Now in such cases, we should first factor the polynomial x cubed minus 3x minus 2, right? And then be easier to sketch the graph. Now to factor this particular polynomial, we could try the values which can be factors of 2. That means we'll try the values like plus minus 1 and plus minus 2. Correct? So let us say this is a polynomial p of x. So in that case, what is p of 1 equals to? If I write 1 here, I get 1 minus 3 minus 2, which is not equal to 0. Let me try negative 1. Negative 1 cube is negative 1. That makes it positive, right? 3. And this is negative 2. That is indeed equal to 0. So that means x plus 1 is a factor, right? So this means x plus 1 is a factor. Perfect. So let's do synthetic division and get other factors. That's the whole idea. Writing the coefficients, x cube is 1. Then the missing term is x square, right? So we'll write 0 for that missing term, the placeholder. Then we have minus 3 and minus 2. We'll divide by minus 1. So let's bring down 1. So you could do long division if you're not very clear about synthetic division. Multiplying with negative 1 gives us negative 1. When you add, you again get negative 1. Multiply plus 1. Add minus 2. Multiply plus 2. Add 0 as expected. So we get a quadratic function here. The quadratic function is x squared minus x minus 2. Now this quadratic function which we just got, right, these are the coefficients, could be further factored, right? So this could be written as equal to, we are looking for a product of minus 2 sum of minus 1. So it is x minus 2 times x plus 1, correct? So we have actually factored, and now we could write this function as 1 over the first factor of x plus 1. Then we have x minus 2, and then again x plus 1, right? So basically x plus 1 squared, correct? So let me rewrite this function f of x as equal to 1 over x plus 1 whole squared times x minus 2. Now actually it becomes much simpler to sketch the function and then its reciprocal. So let's do it. So these drawings are not to the scale, but they really help you to understand the concepts. Now here, one of the zeros, which is of order 2, is at minus 1. So let's say this is at minus 1. The other 0 is at 2. Let's say this is at 2. Leading coefficient is positive. It's a cubic function. So right side up, right? So let me sketch in green. The right side is up. Odd degree means opposite ends. So these are the properties of sketching, polynomials. Now at minus 1, we have double zeros, so it has to turn back. Here we have a linear 0, it will cross. Joining these points, we get our graph, correct? Okay. So that gives you the graph of the polynomial function. Let's call it p of x. This point here is at minus 1, that is at 2. It is good practice to find f of 0. So let's find f of, I should say p of 0, right? So this point. So let me find polynomial p of 0. So if I substitute 0 here, we get minus 2 clearly, right? Minus 2. So this point here is minus 2 for the function x plus 1 whole square times x minus 2. Now let us sketch the function itself, which is reciprocal of this. So we'll get vertical asymptotes at the x-intercepts, which are double zero here at -1 and a linear 0 at 2. Since the graph is positive, reciprocal will kind of look like this. Let us say this is 1 for us. So let's say this is 1 for us. So crossing through this point, it will look like this. On this end, let's say this is -1, this is +1. So these are the points which are invariant points. So here again, we'll have a horizontal asymptote as x-axis. Now the middle part here, -2 reciprocal is -half. So we could actually, let's say these two are corresponding to -1, the invariant points. So we'll have a graph which could be like this. Does it make sense to you, right? So here clearly this is -half, right? So let me write -half here. A local maximum for the function f of x. So that becomes the graph of our function, correct? So we have sketched the graph of the function. Now we'll move on to question number 3, where we are going to describe its characteristics, correct? So here is question number 3. Let me again make a small copy of the diagram. It helps to explain the characteristics, right? So it's kind of like this. We do have two vertical asymptotes, one at -1, the other one at 2. Right? And the right side of the graph is kind of like this. Left end is like this. In between, we have a graph which is kind of like this, where the y-intercept is at -half, right? So that is how the graph looks like. Now let us write down all the characteristics of the function f of x. Domain. So domain is x belongs to real numbers, where x is not equal to the asymptotes at -1 and 2. So at -1 and 2. Range. So as far as range is concerned, we have all the values except for 0. So we have y belongs to real numbers, but y is not equal to 0. Vertical asymptotes at x equals to -1 and at x equals to 2. Horizontal asymptote is y equals to 0. Increasing interval. So the graph is actually increasing from -1 to, okay, so we really do not know the maximum point. We'll make an approximation here that is between -1 and 2, right? So somewhere right in the center. So it could be 1.5, let's say. Let's say the maximum is at 1.5, right? So we'll say it is increasing into interval from -1 to 1.5, and then it is, this is the only portion where it is increasing actually, correct? Rest of the time it is decreasing, and it is decreasing from -infinity to -1, union, we'll say from 1.5 to decreasing to 2, and then again decreasing from 2 to infinity, correct? When is f of x greater than 0? It is greater than 0 for x greater than 2, and it's less than 0 when it is in between these intervals, that is from -infinity to -1. We cannot include -1, union, or you can write or, from -1 to 2, right? So that is when the function is less than 0. So I hope that helps you to explain the whole process. At present, we are not in a position to find the center point exactly. So we'll just assume it to be 1.5, average value of 2 and -1. So we just added 2 and minus 1 and then divided by 2 to get, 2 minus 2 and minus 1, when you add, minus 1 divided by 2. So it is half. It is actually 0.5, not 1.5. I'm sorry. Yeah, from 0.5. Right. So it is at half, approximately. Correct? Okay. So I hope that is good. Now let's move on to the next question. Here is question number 4. Sketch the function f of x and its reciprocal g of x. F of x should satisfy each of the following. 2 x-intercepts increasing in the interval 0 to 2, decreasing in the interval minus 2 to 0, absolute maximum value of 4. Okay, so let's try to sketch the function and then we'll draw its reciprocal. Okay, so we are given absolute maximum of 4. Okay, and 2 x-intercepts increasing in the interval 0 to 2. So it's increasing this side, however decreasing on the other side, but decreasing from interval minus 2 to 0. So let us say we graph a function which is kind of like this, like a parabola, like up to this point. Since we are also given that the absolute value is 4, so to make things simple, what we can do is we can graph a function which is, these properties are of the function f of x, which is even function as shown here. Now let us say these values, since it is, this value is at minus 2 and the other value here is at plus 2. Let us assume that this value here is, you could give any value, let it be minus 2. Okay, now we really don't know what the x-intercepts is for this graph, but it is not really required. We need 2 x-intercepts. So these are the 2 x-intercepts for f of x, right? So I hope that part is absolutely clear. Now let us sketch the reciprocal of this function g of x. So let me now sketch g of x in color green. Now g of x will begin with the vertical asymptotes at the x-intercepts, right? Okay. Now this is maximum, so minimum. Reciprocal will give you a local maximum at minus half, so that could be here. And somewhere we'll have 1, so invariant will be 1. So that gives you the graph of the center portion, where the value here is minus half, correct? On this side, 4, we have to restrict to that domain now. So 4 is the maximum, so 1 over 4 will be the minimum. So let this be 1 over 4. And on this side, since it is positive, function will go on like this. And from the symmetry, we could kind of draw like this. Does it make sense? And the lowest point on should be 1 over 4, reciprocal of 4. Does it make sense to you? So that is how you would actually sketch the graph of g of x. Now, I've already given you the graph. You need to write characteristics of reciprocal function g of x, correct? So include things like domain, range, right? So you could include these things. You don't know really the equation of intercepts, but you could write approximately. You could assume some value here, and then you can write at least the number of vertical asymptotes. Right? And you could also mention increasing and decreasing intervals, and where g of x is greater than 0 and the interval where g of x is less than 0. So most of the time these are the characteristics of our interest. The function here does not really have a horizontal asymptote since its domain is restricted from -1 to 2 as we have shown here. I hope that gives you a good review of a reciprocal of a function. So we have seen it from different dimensions. Feel free to post questions, and if you like and subscribe to my videos, that'd be great. Thanks for watching and all the best.